All right, so we're back, and we want to talk a little bit about the engineering perspective of isolated user mode.
Yeah.
So should we draw again and get going?
Yeah, I'd like to really hit on a couple of topics. There's sort of a coolness to features that we put into an operating system, and a lot of the stuff we get most excited about in Windows is all the GUI likes of things that you put up. I remember one release, I remember staring at it and says, that looks like Nintendo. It was just the colors, because it used to be very kind of black and white and bland, and now it's very colorful. Everybody gets excited about that, but as a kernel level guy, okay, I got to say, I get kind of more excited about the low-level stuff. It's architecture and also engineering. So I thought that for this final segment on the launch version of the IUM talk, we talk about engineering.
Let's do it.
All right. So as people know from what Logan said last time about some of the features and stuff that we put in, this isn't something that is really revolutionizing the functionality people are going to get in Windows 10. Mm-hmm. It's allowing us to add some security in some very key areas of the system, but really build a platform for the future. So in designing this, we thought a lot about how to do engineering that allowed this to create such a platform that we could build on going forward. And so I thought I would just, with the developers out there, talk a little bit about some of those considerations. So
let's do it.
We'll go do secure mode. I'm doing it on the wrong side here. Normal mode. And this is the same diagram that we've been putting up the last two talks. And then we were putting kernel up here, I think.
Uh-huh.
And user down here. And suppose that I want to do what we did with LSA. Now, LSA is the authentication service. This is how we go figure out, is it really you when you give us passwords? And then other things like Windows Hello and stuff also plug into that whole authentication framework. And smart cards, you mentioned those before, and virtual smart cards, which I really love.
Yeah.
I stopped leaving, if I have virtual smart card, I don't find myself leaving my ID to get in the building, my computer at home. And so this is all very cool technology. And so LSA is that really key piece. And LSA, the actual process, .exe, I think it's called, always used to sit out here in normal user mode before IUM. Now,
so this is something that was in existence before, a process that was designed just to check credentials.
Yes, yes.
Got it.
Now, can I show you something on here?
Let's do it.
Okay. So this is a Windows 10 system. And I have Task Manager up here. That's about the only thing that's going. And I'll use Mark Rusinovich's famous little piece of code here, zoom it. And notice this right here. This is a new process, which is like the system process people remember from before. This actually represents the secure kernel. And it's the secure system process. And as you see, it doesn't really have a lot of data because it's not a regular process. It's kind of magical. But let's go look up here. And here's the LSA.exe that I just mentioned. But notice also, as Logan talked about last time, there's a process called LsaIso. And this is Credential Guard. And LSA, you can see the name of LSA there. So LSA, so we'll go back to the diagram here. LSA used to be the single process, but to make it work with secure mode, we wanted to break it into two pieces. And the reason we have that architecture with IUM about breaking things and repartitioning them into two pieces is the secret about keeping secrets and having them be secure is don't put so much code in there that you introduce bugs or you have problems or things you didn't anticipate that let your secrets get loose. And so you want to build a minimal kind of process. And this is what the Credential Guard process is, LsaIso. Now, back to the engineering. Suppose that we're running on a system that an administrator, say in an enterprise, decided he didn't want to use secure mode. He wanted to run the stuff he was more familiar with. Maybe it's because he wants to put debuggers on this. And guess what? You can't actually attach a debugger to a secure process and do stuff. And so he says, oh, I want this to run over here. Well, you could do it a couple different ways. You could say, well, this has two modes in this program. This program will either contain all the functionality of LsaIso, but have it not be secure and able to keep secrets as well. Or you could do it the way we did it, which is you simply run this process, this program, over here. Now, we can't keep the secrets as well as we could if it was over here, but from an engineering point of view, we don't have to have all these different test cases of, well, what if it's merged, what if it's not merged? We take the same architecture. So it's this partitioning. And so in the future, as we look at other kinds of secrets that we want to keep, as we harden, there are a lot of things in the system that we'll continue to harden against different kinds of attacks. And this, we've learned a lot from the work that Logan and his team have done about understanding various kinds of attacks within the Windows system and the Windows ecosystem that will cause us to get this to be better and better. So that's part of our engineering process. And as we look at how to build trustlets, we realize that, and Logan, I think, described this very well last time, you have to have secrets you need to keep and secrets that you can do something with and not just hand out. So if you think about it, if I had, and we'll go to generic trustlets now, so if I have some agent process over here, call it an agent process, and I have some trustlet over here, and this guy has the secret in it. You can't just have an interface to this that says, oh, I'll give you the secret because I'm the keeper of the secrets. Well, how good is that? Because as soon as he hands the secret out,
yeah, you're not getting the
it's out
protection.
there. And no, he can't trust anybody over here. But the agent said, pretty please. No good, because malware could have compromised the agent and said, pretty please. So building trustlets and thinking how people might do that, and we might be able to do a lot more things with different kinds of secrets. There are all sorts of things we talk about. I don't want to mention them categorically because we find that as soon as we say, oh, we could do foo, everybody says, great, and they get all excited, and maybe we don't end up doing foo. So,
but there is a different way of thinking. If you really need something to be secret, and not just something to be pseudo-secret, you should put it in secure. Eventually, you'll be able to put it in secure mode.
Eventually, be able to put it in secure
With
mode.
the understanding that that secret cannot escape those guards.
That's right. So that's why crypto is a really good illustration of stuff that we do. So suppose that I have this nice world here, but really it all works because I have some kind of server somewhere else on my network, like in administration, or maybe up in the cloud, or Microsoft Azure, or even in the Microsoft Office properties online, all the software as a service stuff that we've been building here. And I need this trustlet to talk to this server in order for something to happen. And it's got to cross no man's land. I don't know how to do these skull and crossbones, right? This is danger, Will Robinson. Because I'm going to take my secret information, I'm going to talk to the server with it, but the network and everything else,
it's going to have a hand on it.
And so this is where the crypto techniques that people have developed in the industry, and we have a very good crypto team here, know how to do all this. They know how to say, I have secrets, I can communicate here, I know how to deal with getting keys across and using public key infrastructures to be able to safely communicate from here to here and not let your secrets get divulged. And that brings us to another one of the big engineering trade-offs that this whole platform has. When you think about how I have security, there's two fundamental kinds of security. There's stuff related to security of secrets and the integrity, which are very closely related concepts. And then there is denial of service. And so if you think about this, right before a big soccer match in the UK, I hear how sometimes certain elements of society will use their ability to launch these distributed denial of service attacks and monetize that fact by threatening to take down some big gambling site in the UK. Okay, so denial of service is really an important concept, but that's not something we're trying to address here. And so in our engineering trade-offs, what we said was this. All the normal operating system stuff, and this is where the kernel lives in the kernel normal mode, all that stuff about allocating pages for virtual memory, about deciding which CPU is going to run what thread on behalf of what process, all of that is still here. That still is. I won't put this here anymore. We're just going to put INTOS instead. This is all in the INTOS kernel. All these resource management decisions get made. And the reason we did this is it allows us to build a very seamless experience for the trustlets. The trustlets look like ordinary Windows processes. They have all the same kernel data structures, the kernel scheduling the threads, the kernel schedules the memory and allocates which memory is in or out of the process, just as it does if this process was living over here.
It just has an arbitrator that go between.
Yes, and the arbitrator is so we can keep this integrity of the secrets, not allow the kernel to peek into this. But then I'm now telling you that we did quite a bit more work in the secure kernel than we've talked about so far. So the secure kernel, it has that marshalling for system calls. That was the big part in terms of, I don't know if it's 2 L's in the UK or what it is here, but the marshalling of the data, and Logan described how all that works. It has some other pieces like the crypto piece. And one of the things we did here is, suppose that this process, this trustlet, needs to encrypt data in some way because it's going to send it to a server or something. There's a lot of code in here because it's got all those Win32 libraries. Compared to the code that's here, there's quite a bit of code there. And so the chances, the more code, the chances of my compromising it are more substantial because it has more code. That's a basic principle that we think about.
I see.
Okay? And so suppose I put the keys up here in the secure kernel. And then if this guy has a buffer of data he needs to encrypt before he sends it there or to decrypt something coming back, he never actually has to see the keys. And so the keys themselves couldn't be disclosed even if the trustlet was somehow compromised.
I see.
And so we've done some things like that to try and really reduce the footprint. Now, I was talking about how all the thread scheduling and the memory stuff happens over here. That means we also do a lot of memory management and synchronization checking here. In addition to just checking the values that come back, we have to be sure that the pages that we were told to use by NTOS actually are our pages and are secure. So suppose we have a page that we're using over here and it's in memory, and now we want to send it out to disk.
So the crypto is also in the secure kernel. What else?
Well, we talked about how we left the resource management over in the normal operating system kernel, and you can think of that as how we do paging, or how we decide how to schedule the CPUs, or virtual processors, as it's called in the hypervisor case. And so we have to have some code over here as part of the hardening that does memory management and also synchronization. So for example, in memory management, we might want to take a page that's part of a trustlet and reuse the memory for something else, and the NTOS says, I want to reuse that page.
So a page fault to disk.
Page out to disk.
Yeah, page out,
yeah. And so to do that, we have to get control, and NTOS tells us, I want that page back. We then go encrypt that page using our internal keys. NTOS can then have access to it, so we tell the hypervisor to give it SLAT access over here, so we can now do I/O and copy it out to disk. In fact, a part we haven't mentioned about the virtual secure mode that the hypervisor supports is another important piece of hardware over here. I'll just mention it briefly. It's called the I/O MMU. It's basically like a paging unit, like a SLAT for how devices work. So when you page stuff out, usually it's DMA, it's the hardware itself accessing it. Well, the I/O MMU is controlled by the hypervisor, and you can't get access to do DMA to the pages that are protected over here unless we give it to you. So we don't give you the ability to use the I/O MMU to access a page until we've encrypted it. So when you copy it to disk, you're copying encrypted data, and the secrets are safe. So there are a number of other things we do in the memory manager section over in the secure kernel to really seamlessly integrate with NTOS management. And then here's the one that synchronization that everybody has always asked me about all the time, and I've never worried about it too much, but we made sure it was never a problem. And that is, suppose that I'm running a thread over here. In fact, I'm running, say, 2 different threads, T0 and T1, and they're synchronizing with each other using some synchronization primitive in the NT kernel, which is a system call over to here. So they're using, we'll just call it a semaphore. And so the question was, can I find a bug in this code if NTOS lies and says, oh, you have the semaphore, go ahead and run. Even though you don't really have the semaphore, this guy still has it. And so we built some protection in there to harden synchronization so that we would never be fooled by NTOS that was actively attacking us with synchronization. There are a lot more things. We had kind of a long list of things that we thought up and Logan's team helped us with that we needed to do some hardening over here. So the secure kernel, the main attribute of it from an engineering point of view, because it has some interesting pieces of code in it, is it's not extensible. So in our first talk back in the first of these sessions, we talked about how the Windows kernel was so democratic because we let anybody who would sign their code and put drivers in be able to extend the operating system that way. But the secure kernel is something that we will never let people arbitrarily extend, so that we can always trust this as the way of protecting everything the trustlet thinks it knows about the NTOS kernel will be vetted by this piece of code.
That's remarkable. Well, cool. Well, thanks so much for spending some time with us, Bud. This has been a little bit about isolated user mode, the secure kernel. It's been pretty exciting to see how this stuff's going on. Thanks for watching. Thanks for being with us, and we'll see you next time. Take care.
Thanks, Seth.